Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 16, 2026, about 4 days ago. It introduces a novel framework for constructing neural network architectures that come with rigorous, formally verified guarantees for solving hyperbolic partial differential equations, allowing them to reliably extrapolate far beyond their training data. The paper is titled, Beacons, Bounded Error, Algebraically Composable Neural Solvers for Partial Differential Equations. And as we'll see later, the ability to mathematically guarantee error bounds in neural networks represents a massive step forward for trustworthy computational physics. Figure 1 illustrates the practical workflow, which begins with a high-level definition. The left panel shows the racket-based domain-specific language used to specify the partial differential equations, here the 1D Euler equations, along with the simulation parameters and network architecture. From this symbolic definition, the system automatically generates the optimized C code, shown on the right. This code implements the numerical solver, such as the Lax-Friedrichs method, which produces the verified training data needed to teach the neural network. So while Figure 1 handled the implementation, Figure 2 demonstrates the framework's formal verification capabilities. The left panel shows the final steps of a symbolic proof in Racket that confirms flux continuity for the underlying row solver, ensuring the training data source is mathematically sound. Then, the right panel presents a corresponding proof for the neural network itself, explicitly calculating the worst-case error bound to guarantee the model's reliability in non-smooth regions. Well, moving from the proofs to numerical results, Table 2 presents the conservation analysis for the 1D linear advection problem. Conservation error measures how well the model preserves the total physical quantity over time, which is critical for valid physics simulations. The first two rows show that standard neural networks suffer massive errors which actually worsen as the model gets deeper, exploding from about 500 to over 4,000 in magnitude. Conversely, the beacons architectures in the bottom rows maintain tight conservation, and their accuracy improves with depth, achieving a total error of just roughly 50 in the 8-layer version. Alright, while the previous table highlighted conservation issues, Table 1 quantifies the actual solution accuracy using L-infinity and L2 error metrics. The top two rows reveal a critical flaw in standard neural networks. Simply making the network deeper, going from 6 to 8 layers, causes the final L2 error to skyrocket from roughly 2.5 to over 9. This suggests the model becomes unstable. Conversely, looking at the beacons architectures in the bottom rows, the errors remain consistently low. The 8-layer beacons model achieves an L-infinity error of about 0.63 across all frames, demonstrating that the method improves accuracy without sacrificing stability. Okay, having quantified the errors, Figure 4 now visualizes the performance difference in a 2D linear advection problem. The goal here is to predict the movement of a yellow disk traveling diagonally. The top row establishes the ground truth numerical solution, where the shape remains perfectly circular. In the middle row, however, the standard 8-layer neural network distorts the object significantly. Notice how the disk becomes egg-shaped and lags behind by the final frame. In contrast, the bottom row shows the beacons architecture effectively solving this issue, preserving the correct circular geometry and advection speed throughout the simulation. So moving from simple advection to the more complex compressible Euler equations, Figure 7 presents the results for a shock tube problem. The plots display density profiles at 2 time steps, where the blue dashed line represents the ground truth. Notice how the standard neural networks, shown in red and yellow, fail to capture the physics. They smooth out the sharp steps and significantly lag behind the true wave speed. In contrast, the 8-layer beacons model, the green line, tracks the numerical solution almost perfectly, correctly resolving both the expansion fan on the left and the sharp shock waves on the right. Well, extending these results to 2 dimensions, Figure 8 shows the compressible Euler quadrants problem at 3 time steps. The top row displays the ground truth from a high-resolution numerical solver, featuring complex wave interactions and a distinct protruding ray structure in the top right corner. In the middle row, the standard 8-layer neural network fails to capture these details. It blurs the sharp features, completely misses the ray structure, and even predicts the wrong curvature for the wavefronts. In contrast, the bottom row shows that the beacons architecture preserves the correct qualitative shapes and propagation speeds, matching the ground truth much more closely. Wrapping up, 2 major points stand out. First, this framework transforms neural networks from heuristic approximations into rigorous numerical methods with proven error bounds. Second, by guaranteeing stability in unknown regions, it enables reliable simulations of complex physics that are impossible to validate experimentally. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.